building construction topic, which involves construction technology as well as facades, vertical transportation, and different methodologies for the tall buildings. So, in this lecture series, you are the first one who will be starting the uh, lectures with facade. So,
Fantastic.
a warm welcome to you, and I hope this is a great thing, exercise, a great experience for the students as well.
Yeah, I really look forward to student engagements, and I've been doing this for a while now, and I think this is the first time we're sort of having this virtually. So I'll try and do my best in terms of communicating all the ideas that students should know, and what we typically use in the professional world. So, Parikshit sir, I'll follow your lead. Let me know if it's good to start, then I'll just start off.
Yes, sure. I'll just give you, just give me some time. I'm just waiting for
Sure.
some more student to add. Meanwhile, I'll just introduce you, sir, to our principal. Vinit sir is also here.
Great.
Vinit Mirkar. Uh, Vinit sir, are you there?
Yeah, but yeah, but
Yeah, I think, sir, there is some issues in your mic. We can't hear you.
uh,
Yeah. Now we can hear you.
yeah,
Yeah.
great to have
Good
you.
morning. Good morning, sir.
Good morning, Vineet sir.
Yeah, nice to see you, and thank you for accepting the invitation from our side and giving your valuable inputs and practical and the industry inputs for our students, because that's what we aim for. All the students, like the academia, they have to have that interface with industry uh, within the curriculum itself. Because whenever they go as a professional out from here as a bachelor of architecture and architect, I guess they will be contributing better to the industry and lesser conflict like that. So that's what I guess we can start the lecture.
Yeah, thank you. And I think really happy to be a part of the Go Plus lecture series to start with. I think it's a great initiative by IES because I think it's important for students to know what other disciplines entail apart from architecture. So there is this little seed in your head while you're designing a high rise. There's obviously a whole lot of other disciplines that come into play that you need to be mindful of just to make life of people like us easier.
Okay, I think Saloni, can we start with the introduction of the speaker?
Sir,
Sir, you want to
is,
ek minute.
is
Yeah, sir, you want to add something? I think you were talking something. Vinit, sir.
No. I just said absolutely. That means I was agreeing to what certainly is very important. I guess we share the same the feeling that everybody has to. We have to participate from the academia more or less. That's what the reason is. So that we are more aware. Students are more aware. They are more exposed. So that they can think critically, and when they actually in architect, they have better opportunity to go ahead.
Yeah.
Couldn't agree more.
Good. Thank you. Yeah, Saloni or Ria.
yes, sir. Good morning, everyone. I'd like to introduce Gautam Bhasin to everybody over here today. Uh, Gautam Bhasin is the regional manager at Inhabit Group. He is an architect by training and a building enclosure specialist by trade. His work experiences span the building industry across 3 countries, having successfully delivered engineering solutions across Hong Kong, Macau, Singapore, Malaysia, Indonesia, Myanmar, Middle East, and India. Gautam's specialist
Hello.
skills. Hello.
Ria, go ahead. Ria, go ahead.
Go ahead.
Yeah. Gautam's specialist skills include complex geometry rationalization to arrive at cost effective solutions that are optimized for manufacturing and environmental performances, optimization which enhances occupant thermal comfort and natural daylighting in enclosed spaces. With a team of 230 specialist designers and engineers across 18 international offices, he is delivering multidisciplinary specialist device, which includes facade engineering, facade maintenance, building physics, lighting, and applied site and sound to leading developers, architects, and fabricators across the region. We would like to welcome Gautam Bhasin with a warm welcome.
Thanks. Thank you, Ria. I think I still need to work on that introduction. So, as most of you heard, I'm an architect by training. So, a long time ago, I was sitting where you are sitting currently, still, learning the trade of architecture, and then gradually gravitated towards facade engineering for the love of detailing, for the love of materials, and that's something that's brought me here today. So I'll start off. Can everyone see my screen okay? Just one or two nods would be okay for that.
Yes, sir.
Fantastic. Great. Um, so I've tried to condense whatever I think are the basic core principles of conceiving or designing facades for high rises, for tall buildings. What we are going to cover, I mean, typically I call this presentation of facades 101. So it's almost like an introductory class. I would really encourage all the students to have questions if you want to type them in chat, or if you just want to jot them down and ask at the end of the session. That would be really encouraged. It would be good for others as well to sort of clarify their doubts in the process. So what we will look at today is a brief history of where facades came out to be in their current shape and form. How did glass evolve to where it used to be close to 100 years ago to where it is today, the way it's being used on our buildings. We will understand basic principles. When we talk about high rises are a very different for the lack of a better word, animal. They behave very differently. There is obviously a whole lot of other aspects that come into play when you're designing facades, including interfaces with building structure, including comfort conditions, environmental conditions, etc. And to close it off, we will look at a couple of case studies of very diverse projects which had very different design challenges, and how did we as facade designers or as facade engineers address them. So obviously it's important to keep some basic historical context in play before we start exploring what are the possibilities, just to understand where we've come from. Facades, as we know today, have evolved from a large industrial revolution per se, a large evolutionary process from production to its usage, etc. And glass back in the days used to be something very simple, something very ethereal, something very divine, very limited to be used in churches. Even castles of kings used to have very tiny windows, very small windows, because glass was not available to builders, to people who used to construct buildings as an industrial material per se. So we saw its very limited usages in mosques, in form of stained glasses, in form of stained glasses in churches, which brought in this divine light, providing divinity to the space. Um, glass is glass evolution into buildings started somewhere in close to the early 1500s, where the float glass, the sheet glass that you can actually buy today to use in your windows or doors was not available as yet. So the glass blowing industry in Central Europe was the point of conception of being able to procure glass for buildings. And the simple point was that they would take a blob of glass at the end of a stick, and the image to the right that you can see, they would just keep spinning it till it reaches a diameter of about 3.5 feet, or even 4 feet. And it solidifies, it cools, and then you would just break it at the center point, and that would become your sheet of glass, like a circular disc of glass that you would then use in your buildings. The image on the left shows how that glass would look like. So this used to be called bullseye glass. So you suddenly start seeing these little punts in between. And the only purpose, the pure purpose, was to bring in light. It did not offer clear visibility to the outside, but you could still conceive whether it's day or night or morning or evening. And that's where the Windows utility was limited to. Now, when the Industrial Revolution happened in the mid 1850s, that's when the steel manufacturing was at its peak. We were manufacturing steam engines, we were manufacturing steel girders, large cast iron components, and the picture on the center page is the Crystal Pavilion in the UK. And Crystal Pavilion is a great placeholder for facade engineering today, is because there were a lot of firsts that building achieved. It basically achieved prefabrication. It achieved the first use of glass in an overhead skylight and even on the walls. And given that they didn't have access to the technology that we have today, the entire building was reverse engineered from what was the largest piece of glass that you could cast. Now, the technology being limited, they would have people in an enclosed room which is fully insulated. They would heat the glass to such high temperatures that would become completely fluid, completely liquid, and then they would pour it into a large cast. And by the time it's solidified, they would start rolling it, and when it's completely solid, it's ready to be used. And there were obviously limitations of how big a cast you could make. So based on that, the entire building was designed backwards. And that's what you see here. So all these panels are all in glass, which was casted with this method, which was a simple timber cast that you would pour molten glass into. Then came the mid 1950s. I think glass was still very, very limited to its usage, because Crystal Pavilion was more of a power showcase that this is what industrial world can do, but then it still did not come into play in mainstream buildings. So buildings are still having tiny pieces of glass, or no glass at all, or timber windows for that matter. 1952 came a big revolution, and I think we really owe it to this man. Alistair Pilkington is his name, and there's a glass company that runs by his name now, who invented the float process, the float bath process. Now, glass by itself was rolled, and then they started rolling it on conveyor belts, but then that led to a lot of distortion in glass. So you could see a very distorted image of the sky outside, or if you try to look in, you would see a lot of distortion. So I think the clarity was desired, where you can see this pristine view to the outside or have that visual connect to the outside. So Mr. Pilkington came up with an idea where he basically floated a really semi-solid sheet of glass over a tin bath. Now, tin has a lower melting temperature, so the higher melting temperature of glass always made sure that the tin is in a molten state, and it would just float it over tin and then pull it from the other side. That made sure the glass was really flat, and then the rest is history. Mid 1952 onwards, we've started production of glass with the exact same method, even till now, 70 years down the line. The other innovations that came into play, they basically came in line with the float glass process, where you started adding colors and tints to glass. You started doing inline coating on glass, which gave it higher performance, and then even offline coating. But then the glass is still manufactured with this particular method. Now, while glass was obviously taking baby steps, or glazing technology or curtain wall technology was taking baby steps, construction methodology of how buildings got constructed was taking gallops in terms of what it could do, or what could be done. So from pure load-bearing structures, anywhere between 1902 to 1926, and these are two examples. The one on the right is Bhaus, which you might be familiar with. The building on the left is the home insurance building in Chicago. And Chicago is known to be the home of tall buildings. CTBUH is based there. And this was the very first building. And because it was home insurance building, they wanted to prove to people that a framed construction is as fireproof, as sturdy as load-bearing construction. So this was the first building that used beam and columns and then added a facade on top. Now, facade obviously looks like solid stone, but then they use stone veneers in panelized form to hang off the building. Now, these two started to marry together, where the building facade initially was really small windows, because you had really thick load-bearing walls which need to bring the load of the building down into the ground. But then when you had frame structure, the perimeter of the building really became free. It became unshackled of having to carry down any loads of the building itself. The slabs would transfer the load to the column all the way down to the ground. So the infills, all of these windows then could expand in size. They could grow bigger, which then made it very important for us to start reacting to that as an industry, where we started having ideas of curtain walling, ideas of structural glazing on the outside. Like the Bauhaus one is probably the first stick installed curtain wall system, where they had the entire frame structure carrying the loads down through the column down here. And then all of the external glazing is basically steel sections that have the glass embedded into it, with cap structure on the outside. So this is what was the turning point. So from early 1930s all the way to now, we have really evolved based on the same principles. We have started utilizing curtain walls as a primary external envelope. And purely for that reason, it's called a curtain wall, because it's like a curtain. It hangs on a building. It does not carry any building loads. It suspends itself, and it's supposed to be an individual unit that deals with all the external forces and loads. So from the early 1500s, where we would spin a disc of glass and try and cut little pieces out of it, put them in our windows, all the way to now. I mean, the Apples of the world are basically using glass as a structural component by itself. There's no visible steel, there's no visible concrete. We have started to understand the material a lot better. We've started to understand the processes that make it structurally more superior, environmentally more superior, for us to use them more extensively in our buildings. So that I think sort of sets the context of where we are currently in terms of technology, and how we are going to use that, and based on our understanding, what are the basic principles of curtain wall design or external facade design. So the first component that I will walk through is the outline principles of all the different factors that we need to keep in mind while we're designing facades. So this is what we call as a typical hierarchy of all the design parameters that we need to take care of. So normally what happens is you need to make sure that the facade is structurally sound. It should be able to deal with winds from the outside. It should be able to take loads from the inside if someone leans on it, if a child throws something at it, etc. And it should be able to sustain the building loads moving left and right. It should not warp or it should not D-shape itself. So structure is obviously important because if the facade doesn't stand, the next stage doesn't arise. The next stage is obviously environmental. Facades is our only barrier between the indoor comfort and comfortable environment and the external harsh environments. We want to keep the summers out, we want to keep the rain out, and we want to make sure the temperature is in a livable condition, the humidity levels are in livable condition. So facade is the only barrier that makes sure that you can achieve what you want inside while keeping what's undesirable outside. Um, Finally, aesthetics, which is where your architects come in. I mean, a building obviously has to stand out. A building has to look residential, or it has to look commercial, or it has to look institutional. And high rise obviously have to look iconic because they stand up, they stand out in the city skyline. So aesthetics become important, and facade is the first port of call. That's the first thing you see on the building on the outside. So the choice of materials, the choice of systems, external geometry of the building, etc., that all comes into play. And then finally, this is the toughest of the lot, where we see how expensive is it? Can it be built? What is the cost of putting a facade on the building? So in order of priority, we have to look at making sure it's structurally sound. Moving up, we look at the environmental impact of it, whether we are able to achieve the comfort conditions inside without having a severe impact on the environment outside. Aesthetics, it has to look good. Also, apart from looking good, it has to age well. Like a lot of buildings 10 years down the line, they start looking old. So obviously the choice of materials, the choice of geometry, whether birds can perch on it, whether rain sits on the ledges, etc., is very important. And then finally, cost. Um, in our experience, what typically ends up happening is this. We start with a budget, and this is the hard reality here. So we start with a budget. This is how much I can spend, and here's my render. This is what the building needs to look like, and then I want a LEED Gold certification, and then yeah, you deal with the structure. So what's the right approach is to start with structure, and then obviously look at the cost as an element, and then if required, you revisit the entire cycle again. But unfortunately, this is the sequence that normally gets followed. So one thing that is the most critical in design of facades for tall buildings, for high rises, is movement. Tall buildings move very differently under sway of wind, under seismic impacts, and even as they age, the buildings tend to shorten a little bit, and that's a very small number, but it can be it can have a drastic impact on the design of facade. A good example is what you see on the screen. I mean, rhino is a fantastic animal. You can imagine the ground it sits on is the earth you build on, and any kind of geotechnical forces or seismic forces, the rhino basically just moves around to adjust to them. The body of the rhino, the bones, the muscles, etc., is the structure, and the skin is the facade. Now you suddenly start seeing there are little folds on the skin which basically move around and about. Now they are not restricting the rhino to move; they're actually giving him a very robust outer shell. But when he moves around, the skin folds over and it basically moves around and about, to basically allow for movement, but at the same time give him a nice robust shell on the outside. So we'll look at the first principle, which is the building structure, and how do we cater to different movements or different parameters that the structural engineers provide to us. So structural engineering will be another session for you guys. And a lot of this will link back to what my colleagues from structural engineering team will share with you. So first, very important aspect with tall buildings is wind gets faster. Wind has less resistance at a higher, at a good height. So it actually hits the building face on. And then that has an impact on the design of the facade based on the way the building moves and also the facade's own structure. So facade obviously has to be self-supporting, and when the building sways, like rhino's skin, it has to be accommodating that wind movement within itself without taking any stress or any strain of the building's movement onto the facade element itself. You have live loads that come into play. Suddenly someone decides to put a grand piano next to the window, and that will have slabs deflecting, etc. There'll be user loads where you have a large party and that will have some structural impact. There will be dead load impact, where you have a short-term settling, where the entire weight of the structure will make the building to sink slightly, and the columns will shorten slightly, and there'll be a long-term usage creep as well. Seismic becomes an important parameter, where when you're designing in seismic zones, how does the building behave? How do the floors behave? And what does that translate to in terms of movement on the facade? So we'll look at each of these elements. So normally when we talk about high rises, the choice of system is based on the feasibility of design and installation. And normally when you look at high rises, you see it to be fully glazed, and the choice is not because the architect wants it glazed. The choice is because you want to install something that has the minimum amount of site work involved. So we choose a curtain wall that basically gets installed from the outside. What you see here is a typical panel that moves, that gets installed between floors, and then there is a movement joint. So there's a stack joint which is allowing some movement here, and there's another stack joint that allows some movement here. Now, the vision component, which you look out through, which is the glass, the piece of glass that brings in light, which allows visibility to the outside. That component is anywhere between the floor level all the way to the beam soffit level. Anything above that, that covers your services, that covers your structure, is what we know as a spandrel, or what we call as a spandrel. So that is basically the composition of a single unitized panel, and the joints are really important. That's how you design them, to basically allow for any thermal movements or buildings physical movements or any differential load movements, and I'll come to that in a second of why that becomes important. So the first component obviously is the dead load and live load. The structure will shorten itself over the course of years, and there'll be times where somebody may decide to put an excessive load on top. Parking structures suffer this a lot, where someone decides to park a Rolls Royce next to the parking block, and then suddenly the slab deflects there. The idea here is that if the slab deflects, this panel basically moves with it, and that allows for movement within the stack here, that allows for movement within. So the entire thing, like I said, is the skin of a rhino. There should be enough movement allowance there for you to be able to take any load or any unpredictable behavior of the building. Facade obviously has to be self-supporting. So between floors, you have to design it in such a way that these independent units can deal with external wind loads, can deal with internal barrier loads, which becomes very important in buildings that are public in nature, where suddenly to see the fireworks outside, a lot of people start leaning on the glass. So it all has to be designed for those sort of loads as well. So we talk about fiber stresses in the material. We talk about deflections that should be within allowable limits. Buildings sway differently, so it's hardly noticeable, but the behavior of a building is very different under high wind velocities, where it tends to sway left and right, which means one edge of the building will start to curve, and that will basically make the facade panels start to open up a little bit. So differential story sway, one story may sway by a few millimeters than the floor below, or the one above may sway outwards by a few millimeters than the floor below. All that needs to be accommodated, and that's where the play of these panels comes in. Seismic is another different animal altogether. It's another different building load criteria, which behaves very differently. In a seismic event, the building flows actually tend to go in opposite directions. So one is going left, the one above will go right, the one above will go left. So there'll be like very quick succession movements happening in the building, and then facade has to be designed to accommodate those loads. So these are the outline structural elements that you need to outline structural design criteria that you need to be mindful of. The second component that again is extremely important, because your facades are like the first line of defense for any harsh external environment to the environment that you want to create on the inside. And this is not just limited to the elements on the outside, it's also to do with fire, it's also to do with explosions. I mean, we live in a world full of threats right now. So what if a bomb goes off next to your building? How does that impact you on the inside? So there is rain, which is a factor. place where we live in, we see leaky windows everywhere. So obviously the facade has to be watertight. There are potential opportunities of rainwater harvesting as well, because facade is a really large surface area of your building, and as the building goes taller, the opportunity of harvesting water on the rooftop is very, very limited, but you can actually do more of it on the facade. In terms of solar performance, sun not just gives us light, but it also leads to a lot of heat gain. And the higher you go, the less are the opportunities for you to have outdoor spaces, because the wind can really cause a havoc. So having a balcony at 70th floor is less and less feasible. So the facades tend to be very closed down with very limited ventilation opportunities. So again, you need to make sure that the sun does not heat up the internal space. So sun obviously brings in daylight, but it also brings in thermal gains. There is a large factor called visual comfort as well, because when the sun is really high and you have a large glass surface, suddenly you see there's a lot of glare that comes through. So one easy way to mitigate it is to pull in blinds, but then that also defeats the purpose of having the glass in the first place. And then finally, solar harvesting. We're working on a couple of projects where the clients are really ambitious and they want um, BIPV, building integrated photovoltaics, to be used on the facade so we can harvest energy on the facade. Like I said, a large part of your high rises is the facade. A large surface area of the high rises is the facade. So I think that's again an opportunity that can be used. Um, Safety and security is very important. Again, you don't want to be exposed to your neighbor's mistake that there's a fire in his house and that suddenly starts creeping into your house. There's blast impact and projectile resistance. If there's a typhoon or a cyclone, suddenly a branch breaks off from somewhere, flies in and it rams into your window, what happens then? And then there's wind. So wind obviously has a structural impact, because structure moves because of wind, but also at the same time it has to have an environmental impact as well. Now, where desired, you should be able to achieve an airtight space, and this is very, very important in commercial high-rise buildings where they tend to be air conditioned all the time. So you don't want to lose out air conditioning into the space outside, or you don't want air to be leaking in that impacts your indoor air quality. Natural ventilation becomes important where you have mixed use modes, where you have common spaces, and more especially in residential buildings where people want to open their windows and let the breeze come in. And then finally, it's about occupant comfort. At high rises, at really tall heights, especially sky terraces, etc., the wind can be an uncomfortable factor as well, where it's sometimes too high speed for us to feel comfortable there, because it basically pushes people around. So let's look at each of these elements in a little more detail. So when we talk about the solar factor, or the sun's behavior around the facade, there is two key factors that we consider while designing facades in the tropical climate like ours. One is conduction, where outside is 38 degrees, 40 degrees, and inside is a comfortable 22, 23 degrees. And because that there is temperature difference, there's a delta. The facade will tend to conduct that heat and then radiate on the inside. And that is defined by U value. U value basically defines what is the conductivity of your facade. And the lower the number, the lower the conductivity. The higher the number, the more it is conductive, and the more it actually adversely impacts the performance of the facade. Um, Now, in tropical climate specifically, we are blessed with a lot of sun right through summers, not so much in monsoons, but winters as well. And one of the factors that really impacts the design of buildings here is how clear your glass is, or how much of radiation does it allow to come through. So conduction is purely temperature outside, temperature inside, the delta, and how much conduction happens between the two. And then radiation is one factor where the light shines right through the glass, and then hits the surface on the inside, and then heats the room that you're occupying. And radiation is defined by a factor called as shading coefficient. Now, shading coefficient is directly linked to the performance of your glass, which may have some tint to it, which may have a performance coating on it. And in some cases, because the glass is now being extensively used on buildings, a lot of architects and a lot of environmental engineers and people like us, we even come up with shading strategies where we have external projections or vertical fins, depending on what orientation your building is in. So improving insulation means lowering the U value. Now, by lowering the U value, you would need to introduce lower metallic exposure to the outside. You might want to use a double glazing instead of single glazing. You might want to introduce argon gas infills or other inert gas infills in the cavity. For external shade, for lowering the SC value, like I said, you can actually improve the performance of your glass, but given the extensive use of glass, there may be a secondary strategy of introducing external shading as well, which again lowers the SC value. Now, I know there's most speakers who will talk about green buildings, who will talk about environmental performance as well. They might go into the area of how to orient your building correctly. So I think we work hand in hand with them to find out what's the best orientation, and then we work out what's the best shading strategy for the building. Environment, watertightness is extremely important. People do not like leaky buildings, leaky windows. Water you want to keep out as much as possible. So for that, the facade has to be externally drained. Now, with unitized curtain wall per se, what we see here, each of these individual panels is designed with multiple chambers within it, and we can probably have another class at it in terms of how it actually behaves in an external water exposure. Each of the panels is designed to be drained externally as much as possible. So if the water comes in, it does not come all the way in. There is a few barriers before it comes in, and by the time it goes down, it gets spit out of the building. Another important factor, which is to do with aging of the building, is facade should not have any perfectly horizontal ledges, because in an Indian context, there's a lot of environmental floating dust. There's a lot of suspended pollutant material we have, which tends to sit on these ledges, and every time it rains, it drains down, streaking the facade. So the intention would be to have inclined ledges. Intention would be to have inclined shades, inclined features on the outside, so they have some level of self-cleaning nature. Even having the right materials is very critical. So having coated aluminium rather than marble or other stones, etc., I think that becomes equally important. Air tightness is critical in places where you want them. So there are building typologies where you have very air sensitive, IEQ, indoor air quality sensitive spaces like data centers. Offices are equally sensitive about it because they want to cut back their air conditioning consumption because they don't want to lose that air to the outdoors. There is another new concept that's evolving in residential buildings in high rises, and we've done those in a couple of buildings here, where instead of having operable windows, because if you open your windows, your curtain starts flying, papers inside will start flying, and it'll become rather uncomfortable. So what's now being done is that there's an opportunity to introduce passive ventilation. So there are these little slits in the window system itself that allow a fixed rate of air exchange from outside to inside. So you do get the fresh air. The benefit of staying in a high rise is that you have air is cleaner up there. So you can turn your ventilator on or off based on what your needs are. If you have the air conditioning on, you turn it off. On a day where you want some air exchange happening, you turn it on again. And that sort of allows for a good level of occupant comfort without having really speedy winds running through your apartment. Environmental safety is important, and more so now, given that we've seen so many fire incidents in the recent past. First port of call when we choose facade materials and the high sensitivity involved around it is that we use fire resistant materials, materials that do not catch fire. Then second thing that's really important in use of curtain wall or externally glazed facades is zone isolation. You do not want to be affected by a fire that's actually happening with your neighbor downstairs, or your fire affecting the neighbor next door who may share a wall with you with the curtain wall going over it. So that's again important, and for that we have strategies like floor and room separation strategies. What you see here in dark red next to the slab is where we basically isolate every floor, so it doesn't have any impact of any fire or any smoke that gets generated in the adjacent space. One thing that's sort of increasingly becoming popular, and more so in hotels, which are unfortunately a target of all the terrorist attacks, and also in public buildings and government buildings where there has to be an assessment done of the threat of a blast. So what comes into play there is that, okay, what is the blast impact that's feasible at a certain stage? How far can you filter out people? And then a small bomb that can slip through the security and then it goes off at a certain distance from the building before you can mitigate it. What is the kind of pressures that the building will experience? What happens to the glass? What happens to the system? The last thing you want is a piece of glass flying inwards and then hitting occupants on the inside, and that can be more dangerous than just the blast itself. So the integrity of the structure, the structure's performance under a blast scenario, and also the materials integrity. So the glass has to be a safety glass, which is sandwiched, which is laminated, which allows for that level of pressure to be catered to. Now, something that we are all here for, aesthetics. I think that's really where architects lead the conversation about what kind of materials they want in the building, what kind of geometry they want to express. The building will have its own shape or form, will have its own function, will have its own features on the outside. So geometry again is very important, and geometry in high rises, especially in super tall buildings, is defined or derived or rather parametrically driven by wind studies, so that the shape of the building offers the least amount of resistance when wind hits it. So that helps you economize your structure, that helps you economize your foundations. The experience is really important, and normally in residential buildings, the experience is more inside out of what the person feels from inside, how beautiful his windows from the inside, and then it's also important that what the building looks like from the outside. I mean, we obviously want to appreciate the architecture visible from outside. Materials become very, very important. Vision comes through glass, vision comes through windows, light comes through windows. So those materials become important. The opaque areas are equally important, where you have walls, where you have beams, the spandrel areas, which can be expressed slightly differently. And then there are external features that you can add on, which may be a crown feature on the outside, which may be these really nicely driven, nicely designed external shading features, which give a new definition to your building. So these were sort of outlines of two of the parameters: one, structure, environment, and finally aesthetics. Cost is a completely different subject, and I just probably have one slide to express it. So I think we'll start with how does it get built. So now is the time where we've actually done the entire exercise, and then now we talk about the systems that are used to achieve those visions. So the first thing we do is rationalize the entire building for manufacturing. Facades is the building facades are a part of the industrial manufacturing process. They all come from a factory line. So the more rationalized they are for production, the more cost effective they become, the more easy to fabricate they become, the more faster to install they become. So the job of people like us is sit with the architects, and obviously there's this level of randomness that's desired in a building where you may have different shape and forms, but we try and rationalize it or package it together. And there'll be a couple of examples that I'll walk through during my presentation, which show how it's done. So the first protocol with any building that we design is based on the geometry, based on the height it has, and the system classification of what you can put on a building has an outline of three basic approaches. So for typical high rises, for super tall high rises, or for high rises where really good quality, or where buildings where really good quality is desired, the example on the extreme left is the approach we take. A fully unitized approach is where the facade is designed to be very, very modular. It's almost like Lego, where you get multiple pieces, they arrive on site, you fit them together. So it has minimum interface on site, is minimum risk of failures on site because of site workmanship issues. And the intent here is that the person just comes, fits a couple of brackets, and then he drops a panel in place, and the panels are all interlocking, and that allows you to have completely weather-tight, completely airtight, and a robust building envelope. The intention is to maximize factory So you can do all your quality checks in a controlled environment. It's all manufactured, it's fabricated, it's assembled in a highly controlled environment. So you get a better product on site. And we try and minimize the interfaces on site. The only thing we need to do on site is manage the interfaces. Where it goes and meets the structure, we have to seal that area. Everything else comes pre-built. The advantages of doing this on a high rise is that you do not have to have any external access. Now, as the buildings go taller, it becomes less and less feasible for us to put a scaffold on the outside or have some kind of sturdy external access to basically keep installing your facade piece by piece. So the intention here is that the person sits on the inside of the building and then he just drops and positions it, adjusts it, and then locks it in place. So that's the most popular and the most almost a no-brainer approach for any high-rise building. The possibilities are, if you want to express any other external features or geometry or material, they come prefabricated, pre-arranged, pre-assembled in the unitized panel itself. So once the building starts to piece itself together, then you start seeing the whole picture. The second approach is for buildings that have large projections or balcony projections or structural interferences or structural projections that cannot be avoided. So there we cannot have a continuous vertical glazing, or we cannot have a continuous vertical curtain wall going up the building. For those areas, we would still want to maximize factory finesse. We would still want to maximize the quality that we can get from a factory. So we tend to horizontally unitize it. The interlocking only happens horizontally, and there's a break happening at every floor. So the panels still come and get installed from the inside. The ceiling is done from the outside. And the intention here is that we still try and optimize the fabrication to be done off-site. And there is an interface that we need to deal with on-site. We typically call it a ribbon facade because it runs horizontally, almost like ribbons around the building. You do require partial access in this case. And then the third approach to doing buildings is piecing it together, which used to be the good old way, but it's not very popular anymore, which is to basically buy all the components, bring them to site. So your frame comes as a single little stick. Your glass comes as a separate panel, the window comes in a separate panel, and then you start piecing it together. For this, you require a lot of access from the outside, a lot of reliance on factory, a lot of reliance on site workmanship, which can lead to potential failures. And then you require a full access from the outside, from the exteriors. And because you get frames as individual sticks, this is commonly known as the stick curtain wall system, because you install it stick by stick and then you put the glass in place. So this is the outline of the three sort of most commonly used families. There may be some interface between two. So out of A, B, C, you may have an A1, A2, A3, B1, B2, B3, C1, C2, C3, and so on. So how about the cost? Now, cost really depends on what kind of systems you choose, what is the extent of the application. If the building is really tall, a unitized system, however expensive it may sound, may be actually a wiser choice and may save you more money in the long run. But for a smaller building, a ground plus two commercial building or a retail building, there the choice can be a little more stick driven, because the components can be brought to site. You can still have a robust external access. And then what kind of skills do you have available in the market? India is the labor rich market. Again, the quality is really questionable, but then you get cheap labor. For a smaller application, having a piece together approach makes more sense versus unitizing it. But for high rise, it makes a lot of sense to have a highly modular approach to the building. So that basically sums up the outline key drivers of how do you approach a building's design, and based on what factors do you arrive at a certain decision, which may affect its aesthetic, which may affect its performance, which may affect its size, etc., etc. Now based on these, how do these get applied to different projects? So I have a couple of case studies here, fairly international projects where I was involved in, and how did those decisions get made based on the challenges that came to us. So in one case, there may be a very complex surface that needed to be rationalized or resolved. In another case, there was another issue where the program was really tight, etc. And you will start seeing a few of these system examples being applied on these particular projects. So I'll start with the super tall, given we are talking high rises, particularly for semester 7. This is a project that's currently shelved. We finished the entire design for the project. Um, this is a public building owned by Pertamina Persero, which is the largest oil company in Indonesia. And the building height for reference is about 523 meters, a little over half a kilometer. And at completion, this would be the tallest building in the Southern Hemisphere. So the building is about 523 meters by itself, but what's not really evident is how complex it is in its geometry. Now, the building has an I-shaped plan, and it's a straight extrusion all the way up to this point, which is roughly 320 odd meters, and then it starts to taper backwards. So the I shape also reduces its profile and plan, and gradually also leans back. So there's a twist that happens in the facade. There's a double curvature that starts getting achieved. Now, 200 odd meters is a typical building in Mumbai. Now imagine that building sitting on top of a 300-meter building. So that's a project almost being built in the sky. So we basically got a NURBS curve definition from the architect of how the geometry is derived. And the first problem we identified was, okay, all of this needs to be double curved panels. Now, the intention here is to actually have a facade that's fully panelized. There is no other way you can build something 300 meters up and then for 200 meters more in the sky by piecing it together one by one. So the first problem that we identified was facade's going to be double curved. Now try and imagine a large exercise ball, and then you try and take playing cards and you want to stick them on there or on the surface, trying to achieve the same surface. So the edges will never match because the surface is double curved, and the edges have to match for it to be a weather tight interface, so that the mullions can be shared, so that the frame, etc., can be shared really well. And the first thing we identified was that for us to use really flat panels, because trying to curve panels or trying to bend panels will really shoot the cost up. So the first thing we identified was that if you try and stack panels next to each other and we lean one panel backwards, you would create a gap here by pushing the one edge of the panel backwards. Now, how do we achieve something like that? By making it weather tight, but also keeping it very cost efficient and also aesthetically pleasing, because again, the experience from inside needs to be equally important as it is from the outside. So we looked at a few ways, how do we resolve and rationalize the geometry? So the first thing would be to triangulate the whole geometry for some of the geometry enthusiasts in the audience here, is to basically fold it at a diagonal center, so you can start faceting the entire geometry without having any curvature in the geometry, but then you're still able to span the whole surface. The second alternative is, so now the thing with triangulated geometry is that you have, it's feasible, it's doable. Aesthetics will go for a toss, because suddenly from inside looking out, you'll start seeing a diagonal member running through. So it'll almost look fun. Cost is doable because it's still flat panels and you can still rationalize the geometry to an extent where you don't have to use specialized profiles, etc. The second alternative was to bend it. Feasibility was questionable because not a lot of fabricators, not a lot of glass suppliers can actually allow for that level of curvature in the panel. Aesthetics looks fantastic. I mean, from inside out, it's just nice seamless curved surface. Cost obviously goes through the roof. So again, that's a big question. The other alternative that we explored was window walling it or ribbon facading it. So the plan will have the curvature profile, but when you cut a section, it will have these steps back. Now, feasibility, it's doable. You just need to have that tiny bit of external access to seal it from the outside. It's still unitized to a good extent. Aesthetics will go for a toss because suddenly up above, you'll start seeing a slightly different geometry than the rest of the tower. Cost, again, is doable because it's still panelized, still flat, still vertical. And then the final option that we explored was that if the panel is warped slightly, creating that gap, why don't we fill that gap in between and still panelize it in a way? Again, feasibility was questionable because very few contractors had done it around the world. Aesthetics would go for a toss because suddenly you'll see different reflections of the sky. And then cost again is questionable because there'll be specialized component required at that interface where you have that little triangle getting formed. So we looked at examples of what could we do. So we looked at a couple of our own projects, some other non-inhabit projects abroad, where cold bending was done. Now, what is cold bending? It's basically a glass panel that's warped out of position without using any heat treatment, and it can be done on site as well. So basically, the intention here was to have the two panels that force away from each other to create the geometry, and then pull them and connect them back together by force. Um, and that appeared to be a feasible alternative because it still maintains the cost of a regular panel and allows you to create a geometry by just stressing the panel out of position, which makes it stronger as well. The other thing that's extremely important in very complex geometries, or rather organic geometries, is trying to rationalize panels. So the intention is that every time you have more number or more typologies of panel, it can throw a spanner in the works for somebody who's fabricating it. So the types of the panels, number of panels increase, and every time you have one panel broken, unless you find the replacement of that, you cannot continue installation. So there's a panel group exercise that we did. All of these gray panels in the center, based on the original intent from the architect, were different, were very unique. So each of these gray panels is its own shape and size. It does not have another a cousin or another identical panel somewhere else that can replace this one. And based on just simple stacking and simple staggering of the panels, that allowed us to actually reduce the panel groups to 96. Repeated panels almost doubled in number, and unique panels got reduced to a small fraction of what they were before. So again, it's an interesting exercise that we've been working with architects. Some architects really come up with these ideas themselves, and we basically help them out. Looking at a few other materials. So that was basically a super tall example of how problems in super tall differ from other buildings. Now we look at a boutique example of how a very commonplace material gets applied in a very non-unique way, a very unique way, a very non-common way. This is a project in Sydney, and this overlooks Hyde Park, which is the Oval Maidan equivalent of Sydney. Now the building is here in the center, if it's not clear, and there's these horizontal ribbon features which form the balconies, or form these floor identifiers or floor markers. What's not clear from this image is that the first 3 floors are made out of stone. Now stone obviously comes in blocks, comes in flat panels that you can install on your floor, you can install it on your facade, and it gives you a nice clean flat surface with a stone geometry. But in this case, Tony Owen's team was really hell-bent that they wanted to get this organic shape out of the geometry. Now, stone may not be the most friendly material to achieve it. There's other materials which allow you to achieve a geometry like this with more ease, but stone was really locked in. And the intention here was to actually showcase the material in its own unique form. So the first port of call there was to try and rationalize the geometry as much as possible. And that is to make sure that you always have less panel types and more number of panels of one type. So that's the outline that we always go with. So the intention was to basically slice the building in half. It's bilaterally symmetrical. So if one panel breaks down, you have another spare always to install it back in. And also to reverse engineer the entire facade so that it starts fitting within the bounds of the stone availability as well. So the stone quarry will always give you stone in certain block sizes, in certain cut slate sizes, etc. And based on that, or based on these panelization types and what it can be carved out of, or what it can be machined out of, we basically provided a block schedule to the stone quarry manufacturers, where they basically cut each block to size. And then there was a 5D CNC milling machine, which basically ate away the parts. It's almost like sculpting with a machine. It basically ate away the parts you do not require. And it gave you these 3-dimensional panels, which basically then get laid over a framework module, essentially. And that's built out of tubular modules, which are all bent to shape. You place the stone, you secure the stone. And again, the intention was to have this as modular and as unitized, as panelized as possible, because you can't possibly have a scaffold that starts from the ground, disturbing all the retail environment downstairs. So the idea was to have these panelized. You lift a panel with the framework integrated, with the panels on the outside integrated, and you drop that in position, and that's it. Every floor just has 4 panels that need to be installed. So a truck arrives in front of the building, the tower crane lifts it, drops it in position, and you're done. The truck then drives off. So it's a 5-minute installation process. So these were the rigs that we designed, which basically has just 2 pivot points, which allow you to lift the panel up, engage it with the tower crane, and then lift it up. And then these are the panels that are ready to go to site. So all of these are fully integrated. These are the end pieces, and then there's 2 more pieces that are in the middle, in the center. Now, again, moving back to sort of high rises from the same city, Jakarta. Now this building looks a very plain Jane building, but the client's brief in this case was to have a building that's more experiential from the outside than inside. People who are paying to occupy the building should have a better experience, and it should not be just for Instagram where you take a nice picture, upload it, and the whole world says wow. So the intention behind this building is to have a very clear view from inside, to have as large modules of glass as possible, as minimum interruptions as possible. So the intent here was, when we do a typical unitized curtain wall, now I come back to that whole subject of panelizing the facade. So this is a more 3-dimensional representation of the diagram I'd shown before. So you have a spandrel that covers your slab. You may have a vision that is divided into the bottom half and the top half. And then you have the panels that get hooked on every floor by floor, completing your building ground up. Now, the typical panel widths that we tend to work with, and we also advise that the mullion spacing should be in the range of 1.2 to 1.8 meters. 1.2 works really well because it also sometimes aligns with the ceiling grid of your 600 tiles on the inside. 1.2 sometimes also works really well with furniture arrangements or room dimensions, etc. It could be 2.4, 3.6. Or if you aim to have larger panels, you should not try and go beyond 1.8 meters because that still is within the limits of hoisting a panel. Now, in this case, the client really wanted the building to be more experiential. Like, no, 1.8 does not really cut it. 1.8 is still too many frames vertically. And when you look out, there's a lot of disturbance, there's a lot of visual clutter. And they wanted this. They basically wanted to increase the panel width to 3.6 meters. Now, 3.6 by 4.2 is a really large panel. You can't fabricate it. You can't transport it in a regular truck. You can't hoist it. So how do we make it work? So the whole unitizing principle was then flipped over its head by having to split the unitizing in 2 parts. So you have one panel that goes on the slab face, which is the spandrel unit, and then there is another vision unit that's installed from the inside that drops it in. So what we've done here is, instead of having a tall panel, we basically rotated it sideways. So it's a nice horizontal panel, which still has the same sort of weight that a typical 1.2 to 1.8 panel has, but it allows you to have a slightly wider panel of glass. Now, typically, for commercial buildings, you may have a typical grid of about 8 meters, 9 meters. Here in India, we designed it to 10.8 meters with high seismic specifications. Now, if you were to do 1.8 meter panels or a mullion repetition of 1.8 meters, you would get about 6 panels between your column grid. But what we could achieve with that approach is this: we just have 3 panels between your curtain wall grid, and you can see how seamless the view is to the outside. It's super clear, less interruptions. What is also quite interesting is that the panel that goes below your desk level, this is a commercial building, so it gets desks all the way up to this point. This panel has a chunkier frame, but then the frame gets lighter as it goes into the vision area which you're looking out of. Another one, so that's again a plain Jane where the challenges were in a different place, where you really wanted better visibility to the outside, very high performance facade with lots of shading on the outside. Now we'll look at a high complex geometry and how do we try and bring it within cost limitations. Again, a very important part, a very important aspect of practicing architecture, a very important aspect of being able to make solutions feasible without compromising on the aesthetics of it. So this is a project we completed in 2010. Zaha Hadid was the architect for this, and Now, again, this is in China, and China is a very similar market, a very similar construction industry as we have here. They would really love the concept, but when the prices come back of building a Zahadi building in central Beijing, the prices are off the roof, and then they suddenly start comparing the per square foot price, and it's like, why is this so much more? And we can only afford this, so on and so forth. So I think it's important to then start seeing where the bulk of the cost sits at. What are the more expensive elements? What are the more low-hanging fruits that you can immediately address by changing them slightly without impacting the building's aesthetic much? You can actually bring the cost down significantly. So the intention was, the initial design called for the glass and the horizontal white features, which we call the ribbon cladding, in the same plane. So the glass basically follows down along with the metal cladding. So this has got the same geometry in both the materials. Now, the first question was, does the glass need to be inclined? Probably not. Because by inclining the glass, you increase the complexity of drainage, you increase the complexity of fabrication. By inclining glass, which means it has to wrap and turn around the corners, which means it also has to be bent in shape. It also has to be trapezoidal in nature, which again takes panelization to a really high level of complexity. So the first port of call for us was to actually have the facade installed as vertical. And to express the building's shape on the outside, we still continued to have the ribbon elements running horizontally at an inclination, wrapping and turning and curving around the building, because it's much easier and much more cost effective to work with metals in an organic form rather than glass or curtain wall, which is the functional barrier of your building. If that goes wrong, the building leaks. If that goes wrong, the building is no more safe to occupy. So the intention was to actually have these panels installed vertically, which will seal your building. The building is sealed, which means you can start your fit outs, you can start your interior works, and all of these external panels, all of these external ribbon panels can then get installed in a parallel program per se. To basically explore different methods of installation and how do we address the geometry, we even designed a saddle bracket here, which allows to use multiple angle conditions by just turning the bracket over the saddle, and that allows you to use the same panel but in different inclination conditions as it wraps around the building. So small little details that make a huge difference in making the building more and more feasible. Parishita, let me know if I'm overrunning the time or anything.
No, please go ahead. Please go ahead.
The next one is one of my first projects at Inhabit, and this is a building that was an existing building, and we basically had a challenge of adding features to an existing buildings with brand new materials. We also got to work with a very funky architect who really wanted to bring some nice organic forms onto an existing building, and the idea intention was that since the building is at a real prime location and it's really aged architecturally, it doesn't look that brand new building anymore. Why don't we try and add features to it that gives it that modern look? It completely gives it that facelift that it needs. And at the same time, we try and improve the property value significantly. So one of few of the things that happened back in the days was the architect, the old architect, the building of the original architect, the building did not provide any canopies. So the idea was to also add functional elements to it. So we basically had the two cores coming down, and the architect basically peeled out the surfaces to create canopies out of it. Instead of just attaching a canopy, which is almost like you basically stick a canopy onto it, you basically, what the idea was to basically pull a canopy out. So this is a view looking up the building, and you see the surface, which is all tiles, which basically wraps over and creates this little canopy for you to enter. And then there's also this glass canopy which connects the two buildings. So the idea was to add functional elements, but also to give it slight uplift architecturally, so to speak. So the first thing was, how do you try and add load on a building that's already built? So obviously there was a lot of back and forth between the structural engineers, us, what kind of load do we add? And then obviously the intention was that the building was tiled and the tiles supposed to come on the surface out. So we basically designed this entire steel frame structure, which will have GRC panels on it, which actually is the same surface, the same cementitious surface that you can adhere tiles to. So the idea was to have the same surface running down. Now, one of the key challenges was how do you do a color transition. So the color gradient that the architect has designed was dark ruby red, and the project is called Ruby Court for that reason. You have a dark ruby red on top, and it all the way comes down, gradually changing its color into a warm white all the way down to the base. And these are not mosaic tiles, not your bathroom small little mosaic tiles. These tiles are roughly this big in size. So the intention was, how do you do that on a building this high? I mean, doing a nice transitional gradient in your bathroom is probably easier, but then this is 180 meters up in the air. So the first thing we did was to, start flexing our parametric muscles. We basically did a tool to establish what that gradient would look like, and the architects were a little concerned that they didn't want to see or read bands in it, because if you suddenly change one color, you start seeing a seam, and then there's a new color that gets added, you start seeing a seam again. So we basically did that little transition, little randomness to it. But then how do you do this? How do you pass this tool on to a manufacturer? Does he understand Grasshopper scripting? Probably not. So we basically simplified it into an Excel sheet which got exported, and every time a color had to change, it had a certain parameter that was already included in the Excel. And everybody was nervous, like, you've done it all, but can we see what it looks like? Does it actually work? So we actually did a dry lay of that in the tile factory. So these are pictures from the tile factory in Japan, where you have the dark red, the dark ruby red up here. And this is a quarter scale mock-up showing how the tile color would come down. And the strategy was that you have the tiles pre-boxed, defined for a specific floor. That box cannot go anywhere else but that particular floor, and then the building is complete. I don't have the images of the completed building, which I should actually include here, but everybody was very pleased with the results. I think I'm down to my last example now. This one is a unique building by itself. It's not a super tall, but it has its own complexities. It's only 6 floors in height because of its proximity to the airport. And it has its own level of complexity that needed to be addressed from an environmental perspective, from system selection perspective, from completion perspective, and even orientation became extremely important. So it's not very evident here, but what's happening in this case is you have the building shifts its shape every floor. So no 2 floors are fully aligned. There's a slight incline, there's a slight angle. So as long as you keep flipping through the floor plan, they all keep changing shape. They all become bigger, smaller, and that makes it a problem point for us to use a fully unitized system where you cannot have a continuous facade surface on any of the walls. So if you recall, the second example of the system type basically used a unitized window wall approach, which had, and this is one partial element that's taken out of the building. You suddenly start seeing these slab projections, which create these outdoor balconies or gardens or breakout spaces. For that reason, we had to use a horizontally unitized approach, where we have the panels that come and get dropped in from the inside, and then there is another cladding element that happens from the outside. Now, one of the interesting aspects of this building was this was supposed to be a Green Mark Platinum rated building, and Green Mark is a building rating system out of Singapore, and they have very stringent requirement for platinum rating. The ETTV value, the external thermal transmittance value of the building, cannot be more than 35 watts per meter square, which is extremely high performance building. So purely based on the orientation of the building, the architects had designed it in such a way that they had more shading where they have higher thermal exposure and less shading where they have lower thermal exposure. So the building is perfectly 1 degree south of the equator. It's oriented east and west, and the north and south is the longer elevations, which do get sun, but they get significantly lesser sun than east and west. So the intention here is that the north and south will have sparser shading, so it'll have fins on the outside, but they'll be spaced apart. And as the facade wraps around on the east and west, the density of the shading will increase. So they'll start introducing one in the middle at random locations, and then that swoops around. So the initial intent was to have 6 shades on the north and south, 12 shades on the east and west. We basically optimized the glass to such an extent that they could drop 1 shade from each elevation. So it was 5 shades on north and south and 10 shades on east and west, which again was a very nice sort of balance from a cost and performance perspective. The other thing that's extremely important is trying to rationalize your footprint geometry as much as possible when you start designing it, and always keeping it in the back of your head as a principle. Now, what's evident in this view is that you have most of the faces are relatively flat, but when two flat faces meet at an angle, there's a small curvature to it. So there's a small radius to it. Now, when you're doing a segmented corner, when you're doing a radius corner, the intention is to use flat panels and segment it in such a way that there's different angle conditions when they meet together. And the intention is to actually have minimum angle conditions as much as possible. So the frame typology also reduces, making the building even more cost effective and more optimized for manufacturing. So the first tool we gave and worked with the architects is that when you're turning a corner, you basically use a standard template as a kit of parts. So you have a standard 1.4 wide module that wraps around at a certain angle, making this detail common everywhere. So wherever the panel wraps around an inward corner, you have one frame module there, and wherever it wraps around an external corner, you have one frame module there. So it also reduces the number of component types that you're using on the building. That also is a secret recipe to make it more cost effective and more optimized for manufacturing. So sorry, there's one more. If we have time, Parikshita, if you think that we've overrun majorly, let me know and I can stop at any point. But
No,
I would
please
like to
go ahead.
increase this. I would like to include this one because this has similar sort of geometry complications on a really small scale. So each panel is highly complex, and this goes on a high rise. This is a 320-meter tall building that we completed, I think, about 4 years ago. Tencent owns the building. For all the PUBG enthusiasts, they are the ones who develop the game, and they are the Google of China. All the internet-based services come out of this building. Now, what you see in this view is that it's not a flat surface. And I think the taller the building goes, the flatter the surface is, the more there is a need to start introducing some kind of surface relief to make it appear less flat, because the more flat it is and the more glazed it is, the more imperfections you start seeing in the facade. Again, the reflection into the sky may not be as crisp and as clear. And also there has to be an intention to create some fun in the geometry on the outside. So what you see from this on the outside to the left is a typology which we call vertical sawtoothing. So if you cut the building in section, it has inclinations in section, out or in, out or in. And to the right side here, you have horizontal sawtoothing, and these are all environmentally driven decisions. So a certain orientation will have more shading because of its geometry a certain way. So all of these surfaces are horizontal sawtoothing. So if you cut the plan and all of that facade is seen, then it's all like a zigzag pattern in plan, while the one on the left is a zigzag pattern in section. So like I said, manufacturing is the king. If you make the facade more modular, more efficient, the more beneficial it is down the line for someone who's manufacturing it, the more beneficial it is down the line for the client, who can reap the cost benefits of having it optimized at the front end itself. So the first thing that we tend to do is to try and identify how to address the modularity of it. So we start identifying the type A, the type B, the type C, how repetitive can it be, and then also address the sequence of installation. Because if you are manufacturing type A, suddenly switching to manufacturing type B would obviously need you to rejig your factories, rerun your machines, re-put in the algorithms, reset up your fabrication sequence. So the intention is to manufacture more efficient. It is to manufacture one type, finish all that, and then move to the next type. So the intention here was to actually have the same numbers manufactured that allow you to complete one floor before you move on to the next one. So this is the method behind the madness. So all the pinks are one type, all the greens are one type, and all these sort of cobalt blue are a third type. And this is the building that's sort of now moving up. Well, at the time when it was moving up. Now, each panel has its own geometry, and as we know, gravity works best when someone stands up vertically. If you try and lean outwards or lean backwards, gravity will pull you down more easily than if you're standing up. So that's why all our facades go up vertically, all our buildings go up vertically, so the gravity loads get transferred downwards. But in this case, architects obviously had something else in mind. So the intention was to push the plane outwards to create the funky geometry that we see in the view. So the intention here was to again try and keep it as panelized as possible, not to compromise on the components that define your water barriers, that define your air tightness, that define your unitizing, which interlock with each other. So the intention here was that all of your elements separation from between the outside and inside basically went into the primary frame behind, and all of the geometry fun that happens, which is inclining the glass outwards, was basically a secondary frame on the outside which pushes it outwards, which is connected back to the primary frame. So that allows you to play with the geometry without compromising on the performance of the building. We also tested it out in a factory, trying to see how much time does it take to put a panel together versus the conventional panel. Is it actually more cost effective to do it this way, or rather just manufacture the whole thing in one piece or piece it together component by component, so on and so forth. The second part, which was the horizontal sawtoothing, which happens on the right hand side, that does not project out as much as the vertical sawtoothing. So there we looked at different ways of addressing it without having to use frames to push it out. We basically had an extruded component which allows you to push it out by various numbers. So when you see this component here in yellow, that can be sliced or cut at an angle without compromising on its structural integrity. You can still attach the glass to the outside and you can put together a unitized panel that still has all the robust unitizing principles built into the form here. And then all the geometry fun that can be pushed out happens in a secondary component that gets attached from the outside. So yeah, so that was that were a few case studies. Obviously, there's tons more, but I think these basically covered different aspects and different challenges in sort of a very diverse working environment, very diverse building typology. So in summary, we basically looked at where we started off from, how did glass came to be, how did glass came to be where it is today. We looked at design parameters, which are structural, environment, aesthetics, some brief touch points on costing. We looked at construction parameters of geometry and design, system choices, how do we select system. Cost again is a variable component and that can be a topic of discussion for another day. And then we looked at a couple of case studies. So I'll open the floor if there are any questions. If somebody wants to understand something a little more, I'll be happy to answer.
Yeah, thank you, Mr. Gautam. I think we can open this for the questions from the student. Kadir, you have raised your hand. Yeah.
Yes, I have a question. So my name is
Yep.
Abdul Qadir. In the first case study that you showed, which is the Pertamina Energy Tower,
Right.
there you talked about how you are you're making the facade which has two curvatures, one vertically and one horizontally. So the solution that was given was that you will dislocate one of the corner, you staggle one corner, and then you'll bring back it by force and then join it on the side. Right? So doesn't that put the glass in constant stress and more vulnerable to failure in wind or seismic activity?
Fantastic question. Actually, glass is stronger when it is stressed. And that's the reason why we have glass typologies like heat strengthening, glass typologies like fully tempered glass, because it actually increases the surface stress. And like, imagine if I were to, a good example, if I were to drop something on this piece of paper versus dropping something on this piece of paper, the one that is bent slightly will offer higher strength. So it can actually take wind loads a little better. It can take seismic loads a little better. And, right. And to address, it's not a one point question. It's also went through series of analysis because it's purely not just glass. It's aluminium that twists a little bit as well. So the connection points and the kind of stresses you generate there. There is a silicon that basically glues the glass back to the frame that goes through some kind of permanent deformation, permanent stresses. So there is quite a few questions, and here we basically went back to the industry saying, we think there is X amount of stress in the glass, is it okay or not? They signed it off. There is X amount of stress in the silicon, they signed it off. So based on that, we arrived at a number that can only be twisted 20 mm off the plane.
Right, understood, sir. Also, I had a question about this. The central, there is a groove which is running across the center of the building. So
there's a what? Sorry.
So there is a groove I can see in the view that was shown earlier. So there are two faces, and then there is
this
a
one.
Yes, sir. Yes, sir.
Yeah. Right.
So this particular groove will have more wind load as compared to the other part, right? So the structure system would change over here, or will it continue?
So there's another presentation which is more wind specific, where they basically arrived at the form based on an evolutionary process. So I agree, if you have a cleft like that around the eye, there's a small cleft which will capture more wind, but then the intention was also, which is not very visible here, right up here on the building, there's a wind turbine.
Okay.
So the idea was to channelize the wind up into the wind turbine. So wind coming from any direction, it basically captures it and then generates energy out of it.
Understood, sir. That's it, sir. Thank you so much.
Thank you. Any other
Any more
questions?
questions? Yeah. I just have one suggestion. Can you just give some guidelines to the student about the window openings for the tall buildings and fire safety kind of thing, and the cleaning also around with it?
Right. So I think on an outline, as the buildings go taller, the opportunities to open windows fully become more and more risky, become more and more dangerous. So the intention normally is, and we basically follow some of the very stringent codes that have been designed around, or that have been written around tall buildings. And the intention is to not open a window more than 100 mm when you go up, when you go really tall. And the reason behind that is child safety. So, child should not get caught in it, or something should not slip through it, or a child should not slip through the window. So the operability of windows, again, is questionable at that height. In terms of fire access, again, different countries have different codes, different countries have different regulation, different requirements. The intention is that you let the smoke out. So the intention is that the windows should be openable enough for the smoke to escape. Different countries have different regulations, where some countries require you to just evacuate the smoke and extract people from the inside. Mumbai has this funny rule where they have to have an externally operable window that opens 90 degrees. How they reach such a high window is still highly questionable, and maybe some fire expert may be able to answer that question better. But the intention there is that you can extract people from the outside as well. And that almost conflicts with the regulation, where you should not be able to open the window more than 100 mm clear in terms of space. Just enough for you to get some ventilation, and I think 100 mm is more than enough for you to get adequate ventilation at that height. But then the fire regulatory norms or the CFO requirements require you to open it 90 degrees. So there are systems being designed around it, where you can have an external hatch that only a fireman can operate, just to completely open the window all the way 90 degrees. In terms of other fire related norms, one very important factor is how do you separate your zones, which I sort of covered very briefly in one of the sections, where you have interstory separation, where you provide fire stop at the base of the floor that makes sure that there's no fire transfer happening between the two floors, because there's two aspects to it. One is the fire can actually climb between the facade and the structure, and it can start rising upwards. The second is leapfrogging. So the facade can fail beyond a certain point, because aluminium has a melting point of 600 degrees centigrade, and any kind of peak temperature residential fire goes up to about 1300 odd degrees. So the aluminum tends to fail, and if the panel falls by then the fire can leapfrog upwards and then start disrupting this panel and eventually spread inwards. So the intention is, we do not fight, we do not resist fire. We only make sure that the facade as a component is non-combustible. No coatings should catch fire or cause droplets or cause spread of fire upwards on the building. So I think that's very important. What else was there? Sorry, Prakshit, I lost track of the question.
Yeah, and cleaning.
And cleaning, facade cleaning. Okay, so facade, obviously there's with high rises, the chances to be able to access your windows internally is not only risky, but it also becomes more and more inappropriate, or more and more unfeasible. So you typically have external access systems that allow you to access the windows from the outside, that allow you to access the panels from the outside. And that's not just purely for cleaning, it's also for occasional replacement. When a panel breaks, the intention is you should be able to bring the panel from the outside, put it in position, and then restrain it, and then that is your replacement to the facade. Typically, and I don't think I have much here to show. Typically, the systems that we use are all launched from the terrace, from the rooftop, and then that drops a cradle down. And then depending on what kind of services you have on the roof, there is a different kind of system that you can utilize. Now, typically for a building that reaches up to say 140, 145 meters in height, internationally, the code drives that you can use a self-climbing cradle for that kind of cleaning purpose. And a self-climbing cradle is more economical because it has these davit arms, so these like bracket arms that are fixed and installed on the roof terrace, and that has the cradle that has the climbing mechanism built into it. So it has a winch and a motor inside the cage which a person sits in, and that allows him to move it up and down. Anything more than 160 meters or 145 to 160 meters requires us to be having a more robust cleaning system where the winching mechanism is in the cradle, it is in the machine on the top itself. So you cannot use a monorail that runs around the building, or you cannot use those bracket arrangements that basically pick up cradle from down below. The intention there would be to have a machine which is almost like a mini crane that runs on tracks all around, and that basically then drops a cradle. So up to 145 simple brackets, all good. Above that, you have to have a proper machine. And cleaning always depends on how much space you have on the building. Cleaning mechanism or cleaning equipment always is a fighting point with other consultants or other stakeholders, where you need to have cooling towers on the rooftop, you need to have your solar panels on the rooftop. Even the core gets fully occupied, so we need to start looking at solutions that are feasible, because a machine not only needs to be deployed, it just not only is a static element, it basically moves around to clean the whole building. So you need to have a clear path for it to move around and about. So core again works if there is multiple level changes, etc., but if it's a flat terrace roof, and you can manage to get a 2-meter space on the perimeter, you can actually use a really compact crane that allows you to drop a cradle on the outside. Yeah, apologies. I thought I should have included that, but I mean, that's on an outline. This is how we can cover it. And if required, I think we can probably take up another session on this, on facade cleaning and maintenance.
Sure. No issues. Any more questions from the student, guys?
Sir, Rohini here. I had a question, like in Indian context, the glass heats up the spaces. So what are the methods we can use to reduce that heat gain? Like how do we treat the glass, or what elements we add in our buildings so that it is reduced?
So glass on an onset, I mean, glass is a design decision, right? Almost how much glass do you want in the building starts from, an architect sketching up a building, or maybe picking up some references saying our building should look like this. So glass needs to be used judiciously. And there are ways to mitigate heat gain. There are ways to mitigate environmental impacts on the indoor environment by having a high performance glass. Now, glass, when we started off with the float manufacturing process, we had a very clear glass, which is again very adverse. It basically lets the visible spectrum of the daylight to come in. It also allows infrared to come in. It allows ultraviolet to come in, which heats up the space. So the long wave and short wave radiation basically are the enemies of the indoor space. The idea and intention there is to basically allow visible daylight, which allows you to see the surface, but it does not heat up the space. So the intention is to reflect out ultraviolet and infrared, for which there is a very highly specialized coating that's done in silver oxide. It's called low emissivity coating, what's commonly known as low E coat in the market. Now they've come up with single low E, which is I think close to about 12-13 years old. Double low E is about 6-7 years old. They've now come up with triple low E, which is 3 coats of silver oxide, which basically make the glass extremely clear, allowing it to have a very neutral look from the outside, but at the same time, it's very, very high performance. So you have very low U values, very low shading coefficient. And even then, if you have a very high ambitious performance requirement from the building, you should start looking at how to shade the building at a secondary level. So you have very high performance glass, but also at the same time, you can add shades to the outside. You can add features to the outside. And again, I think it's really important to be very selective about how you use glass in your building based on what orientation the building sits in. So large part of east, west, and south would be really, really important in our country, that it has a minimal exposure. North light, as we know, is great light. So have more glass exposure on there, have less glass exposure on the south specifically, because south starts getting exposed as soon as the sun rises all the way to the west in the evening. So I think there's multiple factors. Firstly, try and use glass very, very carefully. It's a double-edged sword. It gives you clear views to the outside, but it also makes the indoor, it can very quickly make the indoor space very, very uncomfortable and can spike your electricity consumption up from an air conditioning perspective. But if you have decided this is the amount of glass you want to use, there is secondary methods of reducing thermal comfort, well, increasing thermal comfort and reducing thermal gains.
Yes, sir. Thank you.
Okay. Any more questions from the student, guys? Any more questions from the students? Okay, I think this is a great session for the, and you have shared beautiful examples also, because now they'll come to know the theory part is you should thorough with the theory part, but application is most important, and actual construction site logistics are very important.
Very, very important. Yeah.
Great talk by you, and I think even Anuja ma'am is also here, so I would like to thank her for the coordinating everything. Guys, Anuja ma'am is coordinating for all those lectures for you guys, and
hi everyone. Gautam, it was amazing presentation, and
thanks, Anuja.
I've been hearing you for past several years, and from the students' perspective, it was amazing. And I must mention that great questions from students.
Yeah.
And,
very sharp.
I'm amazed, and I'm so happy that all of you are going to go through high rises in a very different way, because all these speakers are the eminent professionalists, and I'm so delighted to be part of this, and it was a really refreshing morning for me. So enjoy all of you with all these speakers, and their knowledge sharing is going to be a great experience. So Parikshit, it was great, and Gautam, as always, it was great.
Thanks, Anuja. Thanks for coordinating the whole event.
Oh, it's a teamwork. Come on, I mean the entire core team.
Yeah. Vinit sir is also here, so I think.
Hi, Vinit.
It was great to have you and participating in the event, Anuja.
Yeah.
Because sometimes we organize something, but many times we don't get the time to participate. And the kind of outcome, which the kind of pain you have taken to arrange this kind of thing. So, and you must be having a kind of slight relief of fulfillment that the students are reacting positively to it. And I should be saying that the Gautam has made that presentation so simplistically, which can reach the students very correctly. I guess that is also an important, that how well he has created a presentation, how well he has reached to the students, because many times it doesn't. You are always in contact with the architects who are more proficient about your language, your kind of delivery. But to come to this level, giving them a rightful thing from the concept more or like a morphogenesis he did from the right from how actually it was evolved, why it was evolved. It is a nice thing to see that approach of a professional when the person is coming to academy and trying to deliver his content and so efficiently. So I guess it is the teamwork as what you rightly said, and it is
Yeah.
definitely helping the students. And I guess these coming lecture series is gonna be making this experience more enhanced and more enriching for all of us. I guess
Yeah.
it is nice to hear and such kind of minute details as a professional. Also. Sometimes you decide in various commitments and business of our profession. Sometimes something gets missed out, but these kind of smallest things also get inserted to our kind of baggage of knowledge. So I guess
Right.
for that also.
So it's a great leadership of Girish Dravid, Subodh Arora, Yogesh Hatte, and Nikhil Sangvi, and me being a part of the team. And I think with their words, all these great, eminent people are going to come on this stage, and great experiences and their own personal project they are sharing, which is, I think, for the students, it's amazing. They are all working on such high rises and such immensely talent what you're going to experience, and keep your questions ready and update yourself. So we are going to create that environment, and you have so much. So when as these series is going to unfold, you are going to experience altogether, it's a roller coaster ride. So at the end of it, I think you will say that once again we want to go on a journey. So
Yeah.
I think that's what the excitement we are going to have for next few days. We are also excited.
Yeah.
Yeah, and just to add to that, I think if there's any intention, or we'd be happy to do any follow-up sessions. I mean, hopefully we can do this in person sometime soon. But if not, if there's a sort of more interest on learning more about specific aspect, I mean, today was more of a an overview of what you need to keep in mind while conceiving building facades. But if there's more specific interest on specific subjects, I'll be happy to run another session.
Great.
Definitely. That would be, and I guess the students will definitely will start posing these kind of queries. And once we get collection of those queries, we will put up, and then we will see how we can actually organize some sessions or maybe small personal talks or otherwise. We try to see and convey to Anuja. She will definitely do that. At the same time, I would like to thank our Professor Parikshit sir, who is painstakingly following this aspect to get these kind of people on board and collaborate with Girish Dravid sir, Anuja, with the CTBH, the whole team to get these kind of interaction with the students happening. And definitely Gauri sir, who has kind of catalyst in every aspect of this. So I guess it was important. So I guess this start has begun now, and I guess long journey to happen from here onwards. So guys, is, thank you very much. Such a wonderful start.
Have a great day, all of you. Stay safe.
Yeah, stay.
Likewise.
Thank
Yeah.
you.
Thank you.
Thank you.
Thanks,
Bye.
everyone.
Bye.
So,
Bye.
hello.
Yes. Sorry, somebody.
So, Hina here. So,
Hi.
I had a doubt. Is there a way to ventilate a high-rise building naturally, or no?
There is. I mean, the idea is that you shouldn't open your windows too far wide, otherwise it becomes extremely windy. There are passive ventilation strategies that you can adapt, where you have ventilators or small slots that you can control. How much ventilation you want in the indoors. If you want to really feel the breeze in your face, you'll have to open the window. But to have a certain amount of air change happening within your apartment or within your room or within your office, there are controllable devices available that you can use in your facades. The intention behind those devices is that you should try and keep the elements out still. You should not get any rain on the inside. There are carbon filters built into it. So if the outside is really smoggy or really polluted, you should keep that out as well. And also there are acoustic baffles. Although sound does not reach, or traffic noises do not reach that far up, but then you do not want to be disturbed as well. So there are those strategies available, and I think we can. I'm seeing more and more interest on those aspects, which I think we can definitely run another session at some point.
Thank you, sir.
Sure. Thank you. Thanks a lot, sir.
Great.
Thanks a lot, Anuja ma'am, Vinit sir.
Yeah, bye. Bye, everyone.
Great. Thanks, everyone.
Thank
Thanks
you.
again.
Thank you.
Bye.
Bye. Bye.
Thank you, sir.
Thanks. Thanks a lot. Bye.